Okay, so let's start. This is uh, this is functional analysis. Uh, uh, and that Manta Institute. Uh, so what's really happening? Uh, uh, this is going to go beyond like typical undergraduate course, and what's really happening in terms of the content. So from my side, uh, I'm more of a guy who teach to learn. Okay, uh, so for I do research on this thing, different spaces, uh, and this has applications to spectral theory and number theory. Right, so this course is mainly focused on kind of going through all the details, background details for this topic. And from your side, uh, you can think of as I'm teaching, so uh, mainly uh, foundations of physics without geometry. Okay, so then there is a parallel geometry course that's happening, and once you have these two, then you'll be good. For example, you won't be able to taking this course is not going to help you understand uh, relativity. Okay, but taking this course will help you understand quantum mechanics. Okay, and now, can I get the charger for the iPad, for the laptop? Yes, it's in the bag. Charger. Oh, this one. No need to talk to you about something a little bit. Give me a second, okay? You'll be downstairs, right? I'll talk to you. I'll come and talk to you in a couple of minutes. So from your point of view, uh, this is foundations of mathematical physics without geometry, without differential geometry. So that basically means quantum mechanics side, and uh, and also this will give you an introduction to uh, uh, like symmetries and mainly theta functions towards the end. Okay? And then I'll have a follow-up course that's more uh, like actually in the function spaces, like Diprat spaces, Hardy spaces. They are like complex analysis, but like second or third course in complex analysis. Okay, so so that's what's going on, and So basically the topics are, so I have topics. So, and first part, these are like the parts. I have the detailed like outline of the syllabus in Piazza. So the first set of topics is about kind of reviewing some topics, and then basically get into the point where I can define mechanical system. Okay, and so and then actually prove some things about it. And so this is very, and the first part is it's a it's a really good exercise in mathematical modeling, and I think this is the best modeling example that we have. Okay, so the this is done by so what's happening, you have quantum mechanics and it behaves in a weird way, and then you, in that case, you want to come up with the mathematical framework to describe it. Okay, so it's like this is an exercise on like building mathematics to explain this phenomena. Like the mathematics is study of structures, and then sometimes you faced with a structure that where you, it seems like you cannot describe it in mathematics. Okay, and then this task was taken by von Neumann, and then uh, so he came up with one thing. I mean, there's like two things: shooting a picture and a Heisenberg picture. And then people are happy about it, and then after a while uh, he came up with another description that's that's more fundamental to the kind of, it starts at a very basic level, and then you get to the shooting picture and the Heisenberg picture, but starting at a very lower level. And the main theorem there is it's called Helson's theorem, and let's see. Not Helson's, Gleason's. So so the first part is going to be kind of getting you to the point where you can understand what this theorem is, like the roughly get to the I'll explain it properly, the what a mechanical system is, and then and they describe what this thing is. Okay, and but you won't be able to prove it, or like you won't be able to fully understand it, but you can understand the philosophy of it. So this is talking about, you give like more primitive definition of a mechanical system, which is in terms of some concept called logic of a mechanical system. And so the Gleason's theorem tells you how you go from there to the shooting a picture. Okay, so it's like you're working under the whatever the quantum mechanics you know of. Okay, the quantum mechanics you describe. I mean, you start with like observable is operator and this and that, and that's not very intuitive. Okay, and we will give a very intuitive definition. Okay, and then work really hard and show that it's you can derive the shooting the picture and the Heisenberg picture from it. Okay, so that's kind of the first part, and then second part we will do functional analysis and and we go through like however much we want, and we'll prove this thing. Okay. In particular, we'll do a lot of spectral theory, and we'll prove the spectral theorem for unbounded operators. Then we'll talk about something called generators for operators, like operator semigroups and generators, and then we'll go from there. Okay. And then when you talk about these things, and the third part is we have symmetries that appears, and uh, I'll talk about those things. So this is basically some representation theory of Heisenberg group. And I'll talk about some representation theory of Lorentz group. Okay, so and once you have the Lorentz group, once you describe these representations, we'll be able to define, we'll be able to give the mathematical definition of elementary particle. And once you talk about representation theory for Heisenberg group, you'll be able to get to theta functions. Okay, and there is something called, you have a representation, there is something called matrix coefficients. And these functions with lots of symmetries, the theta functions, you will see them as it's not about like these variables or the Hilbert space that we're dealing with. It's simply something about the it's about the matrix coefficients. Okay, is defined in the group, not the vectors, right? So what you see as theta functions are actually the vectors, and we'll prove something called Stone one Stone one Newman theorem, and then you go from there. And then the fifth part is we'll talk about contraction. This is actually the kind of the next topics, contractions. And the branch spaces. So this would be like a different course, but it will fit into this. Okay. Now, any questions? Questions? Okay, so ask questions if you don't understand. Like I am actually terrified to teach you guys. So these are not like the normal university students. I know that these are university students and very special. So they are actually from three universities: Colombo, Peradeniya, and University of Morocco. And then they're from Mentor Institute, and they have taken courses at Met in Moscow. I think I think all of you have done like really well, like A's and A pluses, like that. That's like it's real stuff. And so it's not like when you go teach in a university back in the days in Colombo or like in Sri Lanka. So these people have been to the outside and seen the world and see the so okay, I'm a little afraid to tell you the truth. But ask questions, okay? And now, okay, now. So let me not talk the overview stuff anymore. So let me get to the point. So the first one is so the lecture one is about Boolean algebras. And there is a classification theorem for Boolean algebras and like a representation theorem. So it's called the Stone representation theorem, and that's the goal. And then you might ask, like, where does Boolean algebras fits into this picture? And the answer is hello. Is he there? Hey. Okay. මොනවද බලන්නේ? Okay. So the reason for Boolean algebra is this is the classical mechanics. Okay. And this is going to be the foundation for classical mechanics. Okay. And then we'll go through this, and let me draw a picture. So you might have seen two parts of this picture, but not the third part. Okay, so in here you have ordered sets. Okay, it's like partial orders. And in here we have, we call it space. So it's like a set, and things are like we have sets and points inside the sets. Okay. And in here you have algebra. Okay, and what we're going to be doing, we'll be going back and forth with in these things. So you go. Okay, and what's something really good about this theorem is that would be the easiest example of these 6 maps. So, for example, with the algebra picture, you have seen that the algebra and the geometry. So the geometry, as you know, it belongs in here from the way you have seen it, right? And because you talk about geometry, you have points in there. Okay? And then you have seen something a little bit more. You might have seen a way to describe those points as a maximal spectrum of some algebra. Okay, so that's stuff happening in here. So the like algebraic geometry and that type of stuff that goes back and forth between these two. Okay, and there is something in here. I would say this is like the skeleton of like maps between object and its sub-objects. You have sets. If you take for example, in the space, you take a set and then you take all the subsets of that set, and it forms a lattice under the subset relation. Okay, and then some of you might have seen like a group and the subgroup diagrams. Okay. So the group is in here, and in the partial orders world, we'll study the subgroup diagram. And sometimes once you know the diagram, like what's the lattice of sub-objects are, you can recover the object or like get partial information about the object. Okay, and the main reason that I'm bringing this thing in is the second definition of mechanical system that starts here. Okay, so I'm throwing in this, and you're studying this. Okay, and that's it. Okay, and we'll build this picture like really nicely. Any questions? Questions? Okay, so let's start. So partial ordered set, that's a set with the relation with the first property being A is less than A for all A in L, and A is less than B, and B is less than A, and this will imply that A equals B. Okay, and the third one is the transitivity property. A is less than B, and B is less than C, and this implies A is less than C. Okay, and all of you have seen this one, but I'm going to go through like a huge list of examples for this. Okay, and it's so important, and it's ever growing, and I have written it down in the in Piazza. Okay, so the first example, I think I have already shared the link with you. Okay, but if you can have a look at it. But let me go through it. Okay. Let me tell one more thing. So the main text for this course is this one, Geometry of Quantum Theory by Varadarajan. Okay, and he's one of the four, and he's a good role model for us people in Sri Lanka. Okay, so like you guys, so there's four people and four students at one time. IIT. IIT Indian Statistical Institute. Okay, so and Varadarajan is one of them. Varadan is one of them, and then there were two other people and and they were like all four of them were in the university at the same time, and they were under Chandrasekharan Rao, and they are like all his students. And Varadan is a field medalist, and he did probability theory. And Varadarajan, he did league groups. Okay, and he was at UCLA, and he passed away recently. But these are the stories. Okay, so it's a group of students, and they did great things, and they were in India. They were living in India. Okay, and yeah, this is the story I tell everybody, because you have people uh, like Terence Tao, or even like Manjul Bhagavan. Like Manjul is not, I mean, he has the Indian origins, but he didn't grow up in. I think he didn't even do undergraduate in India. Right? But these four people, they're like, in Indian Statistical Institute, and they were doing stuff. Okay, just like being in a hostel in Sri Lanka. Okay, and okay, so yeah, so Varadarajan is the guy. Okay, so and there is a Wikipedia article about the four, and and look into that, and these are like really good role models. Okay, and they don't have uh like they were doing these things since age two, or like that type of stuff. Uh, but also they didn't work with yeah, they were like studying inside in the India, and I think Varadan is uh, still living, but Varadarajan passed away, and mm, yeah, uh, yeah, these are the real one for us, real role models. Okay. Now, so let me go through the examples. Um, you guys can see the examples, right? I made a pizza post, but I'll write them down here, and this is going to be like a very big set, very big list of examples. Okay, so the first one is, of course, we have rational numbers or real numbers under less than or equal. Oh, coming back to this, the reason I went up here uh, is this. Okay, so when you look at the definition of the partial order, what I put in here, what we have in here is this symbol, strictly less than. Okay. And but in reality, it behaves like less than or equal. Okay, good. And the reason for picking this is the notation that used in here. Okay, good, good. But I would of course write things like this. I would write Q under less than or equal. So once I write this pair, whatever I put here, which is normal, like usual less than or equal, that satisfies the property axioms for this guy. Okay, good. And there might be some, I might make a mistake, but it's easy to fix. Okay. And the reason that I'm doing this thing is I'm following the this textbook. Okay. So everything like kind of the old, I will go around and like pick easier ways to describe things. And this book you cannot read from like cover to cover. Okay, for you guys. So I'll like whatever I'm doing is like a couple pages of the book, and but I'll give a lot of motivations and all that. Okay, so we'll be like spending couple of classes just going through 2 pages. Okay, and then you cannot start from the first page either. Okay, so but the main theorem there, I'll prove it. So the Gleason theorem, but the structure is from that book, okay? And good. Okay, now so let's go. Let's go. Okay, now it's getting so all of you have seen. I assume all of you have seen partial orders, and this is a good example. Let's not talk anymore about this one. Okay. Now let's go to this one, the second one. This is power set of x under the relation subset. And here x is set. Okay. Okay. And this is uh, this is a partial order. And then you have 2.1 is a cofinite sets of a set x, cofinite subsets under this. In what you have here, so CF of x denotes the is the, let me write the definition. So this is CF of x is not all the subsets, but subsets of x such that A is finite, or A complement is finite. Good. And then these are 2.2. This is, let me call it CC of x. These are like not standard notations. And here, CC of x is that A is countable, or A complement is countable. Okay. We have this one. Yeah, I think, let me write this one too. So this is B under subsets. Here B is the collection of linear independent vectors. Sets of linear independent vector in a fixed vector space V. Okay. Now, when you look at this and you want to verify, let's say everything in 2 and 3, okay, and notice that these things are boring, okay, and it's boring to verify, okay, and kind of the thing to do in this case, what we have is actually this. Let me call this thing exercise 1. So these exercises, so it goes in the lecture 1. I'll put them in the lecture 1 in Piazza under the lecture 1. And some of them I'll write, add more details and everything. Some of them will be like just like this. And you write the solutions and put it in Piazza. Okay? So if you have 3 kids, you just like answer, like you divide the problem set by 3, like 1, 2, 3, 4, 5, 6, and so on. Okay? Mode 3, and then write down solutions and you discuss in there. Okay? Good? So this is the first one. So the first one is this. So if let L this thing be a partial order, and let L prime be a subset of L. Then L prime, and then you restrict the partial order to the L prime cross L prime. Is also a partial order. Okay. Let me use this. So you restrict the original partial order to L prime. And if you prove this one, okay, and it's very easy. And then once you have this, you realize that if this is a partial order, all the subsets are partial order, and these guys are just this collection of sets are just subsets of this. Okay, so you're not changing the actual relation, you're just restricting the number of elements. Okay, and that's what's happening in all these cases. Okay. And even in B, this is a subset of power set of V. So very small subset. Okay. Good. And the more interesting thing is actually this. I'm writing this a long list, but once we discuss more properties of partial orders, these would be examples of like, let's say this would be a lattice and this is not going to be a lattice and so on. Okay. Good. So let me go back into the my list of examples. Uh, this is a funny example again. So we call these things FAB under subset. Here, here FAB. These are actually these are partial functions. So these are functions from A prime to B, where A prime is a subset of B. Okay, so this is called partial functions. Okay, and actually it is easy to see that this is a partial order, and you kind of have to worry about like what is this symbol doing here. But if you take two functions f1 and f2 partial functions, what do you mean by one function is a subset of the other function? Okay, you think about it a little bit, but what's really happening? If you look at the definition of a function, function is a relation, and the relations are subsets of the product set. Okay, so recall. So relation R on A cross B is just R is a subset of A cross B. Okay, you remember this? And then the function is special type of relation. Okay, and so and then the is this clear? Is this clear? This is clear, right? So the remember the function is a relation where for any element in A, there exists unique B such that A is related to B. Okay, so the definition function f f is a subset of A cross B, meaning that it is relation, and for all A in A, there exists a unique B in B such that A is related to B. This is the relation notation. And we write this thing as f of A equals B. Okay? Good. And then when you think about partial functions, you can view partial functions. Like ideally, this thing would be a subset of A prime cross B, but A prime cross B is a subset of A cross B because A prime is a subset of A. Right? So we can throw all these FABs, and let me put a delta here, okay? Because later on I might just use FAB to denote the functions from A to B, but these are like partial functions. So all these partial functions are actually subsets of A cross B, and so you can compare the functions, and actually you don't have to prove anything that this is a partial order because you can use exercise 1. Okay, any questions? So in here, let me double check. Say we have a function f1 is less than f2. So what does this mean in the like describing in the functions world? So this would exactly means domain of f2 contains the domain of f1, and on the domain of f1, two functions agree. Okay, so the picture here is this. So this is A and this is B. A partial function would be something like this. And then another function would be like something that's bigger would be, you can have another function that's like, there's more points, okay? It's defined in a larger set, okay? It's a simple thing, but so these are examples from topology. And so this one, 3.1, you have this, O and subsets. And here, this is the collection of open sets. Let's say in Rn. Okay. So all of you have seen topology in Rn, right? And I'm going to define topology in general in a bit. Okay, and let's say this one. this one is it's again the closed sets. Okay. The fact that these are partial orders is trivial because the whole power set is a partial order and these are subsets, but kind of the importance come from they would have different additional properties. Okay. And then 3.3 and so these are like CO. These are sets that are both closed and open in Rn. Okay. And then you have examples 3.4, 3.5, and 3.6. Instead of in Rn, we talk about general topological space. You have X tau, and the open sets in X tau is going to be a partial order, and similarly the closed sets and also the clo-open sets. So the sets that are both open and closed are called clo-open. Okay, and all these things would be partial orders. Again, I'm writing this full list because they would have like very different additional properties. Okay, now, and this is really good. Okay, now the next one is geometry. Now, the first one, so this is not 3.1, this is 5.1, 5.2, 5.3, 5.4. Okay, and this is 6.1. Again, we'll spend a whole lecture on this thing, lecture 2. Okay, and this example. Think about this. We have, let me call it H and belongs to Silva. Okay. And here, H is points, lines, and planes from, we call this thing high school geometry. Okay. And this symbol means P point lies in line. Okay. Or like a line lies in a plane A. Or like point lies in a plane A. Right. And this is a partial order. Okay. Again, the proving that it is a partial order is actually trivial because again, like these points, lines, and planes are subsets. Okay, and but we will dive really deep into this thing. Okay, because when you that's why I say like high school geometry, there you draw pictures and put lines and the points and become so trivial, right? And okay, so the second one is again from geometry. So here V and subset here V is the collection of of zero sets. For a set of polynomials. So this one, like earlier you had like lines and points and plane, they're like very straight. But if you take a polynomial and then you look at the zero set, for example, you take y minus x squared, and then you look at the zero set of this. So this is pxy. And then you look at the points xy, such that pxy equals 0. Now that's the parabola, that's a curve. It's not a line, but it's a curve. And you can define if p1, p2, dot pn. It's a collection of polynomials, and then you define the zero set x1 up to xk. So let's say these are polynomials in k variable. Okay. Look at these points such that the pi of x1 dot xk is equal to 0 for I equals 1 to all the way up to k, all the way up to n. Okay, good. And that's geometry too. So I mean, I haven't given you the definition of a geometry, okay? But there you think of this as all geometric things, and if you can like sense it, the definition of geometry will be coming from the partial order side, not from the and these would be examples, but the definition is not going to come from these from the actual descriptions. Okay, good. And but the point, thing to notice for now is how you will. I mean, these sets form a partial order, because you can have one curve sitting inside the like curved surface and so on. Okay, good. So like in other words, I'm kind of what I'm doing, I'm taking things from the space side. Okay, these examples from there, and then I show that they actually form examples in here. Okay, and we'll go the other way. So that's lecture 2. Okay. and it is something really fun. So like in vector space, so the vector spaces are in here. It's a space. Right? You have the sets and the special types of sets, right? And in here we define dimension, right? And we'll define dimensions in here. Like once you define what a geometry is, and then you define dimension, and the definition works for both of these cases. Okay, it's going to be like super fun, and it's going to connect a lot of things. Okay, and I want you to kind of start. I want you to be familiarized with the partial loaded side of things. Okay, so for example, you'll do things without points. Okay, so we'll talk about topology without points, and we'll talk about yeah. So the key thing in the lattice, we don't talk about points. Okay, and then when you're in the space and sets, you verify all these little properties by going into elements always. And we will not have a notion of that in the case of partial orders. But I mean, the main theorem of Boolean algebra is about how you go from just a partial order and then special type of partial order, and then how to recover the points. Okay. So, but okay, so let's keep going through the list of examples. I mean, these things are trivial, but kind of the scope of things should scare you. So the projective stuff. Um, so in here, this is the first one, 6.3.1. That's we have call it L of V and subset here. Here L of V is the collection of subspaces. Of a vector space V. Okay, and this is again a terrible notation. I'll put a delta here. Okay, and this is because the proper notation, the proper use of L of V is the linear transformation from E to V. Okay, so and this is a collection of subspaces of a vector space V, showing that this is again a partial order is just follows from that proposition we said, because these things are just some subsets of the of V. Okay, and then let me draw a picture here. So how you go back and forth from the, like in here we have like subspaces, like lines, points, and planes, and I'm calling this thing as geometry 2, and I'll show you like how these two things connect, right? From the high school geometry, line and points, lines, and planes, and how do you go from there to subspaces? Just a picture, okay? We'll get into details later. So let's say this is your this is where you do you this is where your lines, points, and planes and so on, right? So this is your high school job, and you go up a dimension. So this is 2, and then you go to 3 dimensions, and then you pick the and you pick the origin that's away from that plane. Okay, and then you kind of let's say if you have a point in here, this is a 0-dimensional object in high school geometry, and the line is the 1-dimensional one, so on. So what you do, you connect it to the origin like this. Okay, and then we have we have this line which is sitting in a very troublesome direction. Okay, so they have this line here. So it was this line here. and then you connect it with the with origin again. Okay, so the whatever the high school geometry had here, these are called affine geometry. There's no origin, and but when you add the origin and move away, and then you can consider these like, and from this construction you can map points, lines, and planes and all these things to a higher dimensional object, which is a subspace of a vector space, and then you can go back and forth. We have these collection of subspaces, and you take the intersection with this red hyperspace, and then you get your affine stuff. Okay, so this type of things are called projective. So you go up a dimension, but okay, you go up a dimension and you move from these originless things into one with origins, and then you can recover, go back. Okay, and we'll talk about this in detail. Let's go 6.3.2. So this is again a very, very important one. L of H. Here, L of H is the set of closed subspaces of a Hilbert space. It's okay if you don't understand this, and but I have to write it. This is an important example. Okay, and okay, and then 6.3.3. This is L of X, and this is closed subspaces of a bunch. Okay, and you get sleepy? I think you look sleepy. You know, it's morning for me, but it's night for these guys. You know the danger of falling asleep when you study at night? So back in our days, you'd have like these kerosene lamps and you'd study under that light. And if you fall asleep and if you drop the kerosene lamp, and you can set everything in fire. Okay, you go. Now, this is a good one, okay? Call it L of G. So in here, L of G is the set of subgroups of G. So you have a group, and you have this is the subgroup diagram, and it has some properties, additional properties. Okay, and then you have this one. These are very important. Okay, I'm listing this thing down, and even though these are very trivial to verify, but I hope you will get the idea, like this is going somewhere. Okay, and I of R. So in here, I is the set of ideas. In a ring. All these things fall from still from that lemma, but you can, you have to add additional properties to the partial order to make things very interesting. Okay, and then these would form like different kinds of example. And the 9 I of A subset here I is the set of ideals. In a given algebra. A over some field F. Okay. And okay, so that's the kind of and there are more examples, and I'll go through them. I'll go back and like add more examples to it. It's easy to do. You can add a page, okay? But for now, let's move on. So we have partial orders, and we have like a lot of examples. Okay. So now let's move to the next part, the total ordered set. Totally ordered. So the definition is this thing is a partial order it's partial order, and we have this property for all A B in for all A B in L, A is less than or equal to B, O B is less than or equal to A. Okay, so the elements are comparable. So here is a example. If we take the L to be power set of say of 2 elements, set it to 1 and 2. So you'll have power set of this set with 1 and 2. Just the set that has 1, 2, and the empty set, right? And so that this is a partial order, but it's not a total order. Okay, so because these 2 elements, this one and this one, they're not comparable. Okay, so the total order is something like a line. Okay, so this one not a total order. But if you take L prime, it just has a empty set. So it is just the empty set with 1 and set with 1, 2. And this is my set and under subsets. So this is a partial order. right? So this set would be like just this part of the ledger. Okay. Now, and then you have this guy definition. Now we're getting into interesting stuff. Well-loaded sets. And so the well-loaded sets total loader such that for any subset in here, A has a least element. Okay, so that means there exists some element. That element belongs to the set A, and any element in the set A is greater than or equal to that element. Okay. Now, in here we have something very interesting happening. So let me give examples. So if you take say 0, 1 interval and less than or equal. Okay, this is a subset of R. Or like we can just take this as so we have R under less than or equal, and this is not a well-loaded set. This is a total loader, but not a well-loader, because if you take A to be this set 0, 1, this doesn't have a least element. Okay, so I mean, this is a not example. Okay, so that's not a example, but this one. So the integers under less than or equal. This is kind of the prime example. Okay. So if you take any subset of integers, and you can find the least element. Good. Now, here is a very interesting thing. Interesting property of well-loaded set property. We can define next element. So for any element in A in a well-loaded set, we call it W. In a well-loaded set. If A is not equal to the maximum of W, then we can find the next element. Then there exists unique B such that A like notice now what I'm doing here. Okay, so I'm putting this thing here. Okay, making this tiny. I'm turning this thing into not putting less than or equal. Okay, because I want to use the both symbols. Okay, good. Such that A is strictly less than B, and for all C in W, if C is if A is strictly less than C, then that C has to be greater than or equal to B. Okay. That is teaching. Okay. So
Like first, can I have the iPad?
no, that is teaching forever today. I'll give you the iPad in 2 hours. Okay. So yeah, so this is a very interesting proposition. So this is allowing you to do kind of doing the next element. So the proof is very easy. So you consider the set A. This is the set of C such that A is strictly less than C, right? And since A is not equal to the maximum, so we know that A is not equal to the maximum of W, we get A is a non-empty. Now then you apply the property for the well-loaded sets. Okay, so if A is not equal to the empty set, so this will give you there exists B such that B equals to the minimum of A. Okay, you take the elements that are strictly bigger than A and you take the minimum of that. And that plays the role of next element of A. Okay, so verify. Need to verify 2 conditions. A is strictly less than A is strictly less than B. So this is okay because B belongs to A, and all the elements in A are strictly less than A. Oh, it's strictly greater than A. Okay, so this one is fine. And then the second property is if you have element C, let C be now a set such that C greater than A is C greater than A. And so this will tell you that C is actually the element of A, right? And but since B is equal to the minimum of A, this will tell you that C that B is actually less than or equal to C. So that was the other property you had to verify. And
So I
then
have a question.
this doesn't look like much, but this is huge. Okay, so
Excuse
have
me.
plus 1. You can add 1 in well-loaded sets. Okay. Whenever you can add 1, and then you can use induction to add n of these things. You keep repeating this thing. Okay, so you can add n. And you do, if you have add n and you add n m times, that would give you multiplication. And then you have the multiplication, and then you multiply by m n times, and you get the exponential. Okay, this opens up this opens up arithmetic. Okay, so can do arithmetic. We can do arithmetic in well-loaded sets, but Nitika, you can always stop and ask these questions. Okay, so let me go back here. So Nitika is asking why we can use that the minimum of A exists. This one. Okay, so the property of well-loaded set is by definition it's a total loaded set such that for any subset of A, for any non-empty subset of A, that for any non-empty subset of A in L, if you take any non-empty subset, that set A has the least element. Okay?
Oh, so
Yeah. And good. And that's what we used in here in this proposition, like showing that you can actually do +1, find the next element. Okay? And I'm just writing this thing down. It's kind of convincing you that if you can add 1, you can add n, and you can multiply, and then you exponentiate, and you can do whatever the next thing is. Right? So you have the arithmetic. Okay, so and that subject is called ordinal numbers. Okay, and it originates from here, and we will touch it. Okay, but we are developing the tools that need to the tools that we need. Good, and what we are actually going towards is the main tool in this side of the picture, in this world. That's the Zorn's lemma. Okay, in this world, to do things, we need the Zorn's. Actually, the Zorn's lemma belongs in here, and we use it in all the other places, but we create a partial load and then we apply Zorn's lemma. Okay, good. And we'll get to the ordinal numbers, okay? And so we kind of descending down, and it's going to be a little tricky. Okay, now definition. Let L be partial order. And let X be an element in here. So we define this guy with the set of all y in such that let me change it to this. Okay. Y is strictly less than x. Let me call this thing exercise 2. So you take a partial order and then you look at all the elements that are strictly less than that element. Okay, and then if this thing this is a well loaded. Then you take this one and then you compute the successor of this thing and you get back x. So this unique element like the unique next element, and let's denote it by S of A. It's the successor. Okay, and this is telling you that if you take a well-loaded set, if you take pick any element and you look at the elements that are strictly less than that element, and then you do the successor of that yeah. I haven't defined the successor for set, right? But you can do it easily, okay? Because you take a set and then you look at all the elements that doesn't belong to that set, and then you look at the minimum of that, okay? Good? Yeah, so the yeah, okay. So call it exercise 3. And you have the exercise. No, let's keep it exercise 2. And I'll define what it is. It's easy. here S of a set A is the minimum of we do a set, then it's not going to be the one that we want. We just do a set, and then it's not going to be the one that you want. You want to take the complement and look at the minimum, and you might not pick it. So it's good to do it just for the things of this sort. And we will define something called initial segment. That's the correct notion. But for let me define what this thing is. Here, this is the minimum of set of y such that y is greater than x. Is a C. Right, so and this greater than is strictly greater than because I have used this here. Okay. Good. And good. Now, any questions on this? So, I mean, if we draw it like this in a line, so this is saying that if you take element x here, and then you look at everything that's strictly less than x, that's this guy, and then you look at the elements that are strictly bigger than I think what I want that are strictly bigger than the elements in this set. Let me do this definition. Let's do it for the set A. Here definition. We have a set A in L, and then you define S of A to be a set of Y in L. Such that for all x in A, x is strictly less than. Okay, so these are the elements that are bigger than all the elements in A, and let's call it S delta, and S of A is the minimum of S delta A. Okay. When it is not empty. Okay. Okay. So now we can show this, prove this exercise. Okay. Now, let's connect this. Have you seen the Dedekind cuts, the construction? I mean, this is exercise, but like what's really happening in here is if you take, okay, this example, if you consider rationals and less than or equal, and if you take a element x, a rational element, okay, and then you look at everything that's greater than that element, strictly greater than, and then you take the minimum and you'll get x, right? But if you look at if you look at a set like this, A, if you do the set A, some rational numbers in Q, such that R squared is greater than 2. Okay, now this is a subset of rationals. And then you take the, the point is that the Q is not well-loaded set, and you can take the minimum. Okay, but in the case of well-loaded sets, you can look at you can have a notion of a cut. Cut is sets of like this format. They kind of they don't have a kind of the smallest element, but it looks like they're the ones that are strictly smaller than something. Let's to match what I was saying. Let me put it this way. Okay, and the point is, like, you can define these things purely in terms of rationals. This set and but there's no maximum element of this set in the rationals. And actually, if you look at the collection of these guys, and then you can recover, you can construct the reals. Okay, so let me write this thing. Exercise. This is a good exercise. Let's do this thing. So look at Rudin, baby Rudin. Okay, and the question is this. So let C be the collection of cuts of Q, and show that C is a total order Okay. So, and the point is the Ruding's construction has way of adding these cuts and so on, but we are not going to go into any algebraic properties. Okay, you can do this thing in the just using the partial order. Okay, so you take the cuts, you take these well-loaded sets, and then you take the cuts, and that thing is also going to be totally ordered. Okay, and you can prove that exercise 4. And you can notice that for any well-loaded set, you can define cuts, and you can show that C applied to C is actually C. Somehow, like what we did here is somehow like complete. Okay, you good. These are the. I mean that thing is a little goes through like a couple of pages, but just to do this thing, it won't be too much. And we are going to use the notion that's very similar to cuts. See, the cuts are done in totally ordered sets, and we'll have something called initial segments that are in um, well-ordered sets. Okay, but I want you to mention that this thing is there, and this is a very key part of the undergraduate curriculum. And we have like two ways of constructing reals from rationals, and the one of them is this, uses the partial ordering, and the other one is through Cauchy sequences. And the Cauchy sequence one we'll run into it when you do more functional analysis. Okay, uh, now, okay, it's theorem. Uh, this is very really interesting theorem. So I said that integers are well-loaded sets. Okay, but also if you take numbers from 1 to 25, that's also going to be a well-loaded set. Okay, and if you take any subset of that numbers from 1 to 25, you can find the smallest element. Okay, now, and then you have 25, and you can do this thing with 27, and the kind of 27 is bigger, and it contains 25 as a kind of subset. Okay, right? And it looks like all these well-ordered sets, they actually sits inside each other. You can embed one well-ordered set into the other. Okay. So, and this is somehow somewhat uh, trivial in the case of integers. I mean, if you're using integers in, we're not going into the axioms of integers, then you cannot prove it. If you're not going there, you cannot prove it, and it's obvious. But if you go into the axioms of integers, then it is actually a theorem. But let me write down the main theorem for well-loaded sets. So let be two well-loaded sets. then alpha is isomorphic, O one set is isomorphic to an initial segment of the other one. Okay, so there's few words. So the isomorphic means I mean the first we can talk about yeah, isomorphic means it's a bijection and that respects the ordering. It's like a map F going from alpha to beta, and if it's a bijection, and then if A is greater than B, then the F of A is greater than F of B. Okay, and in here, initial segment means if X is an element in, let's say, alpha, and the initial segment, let me call it P of X, is set of Y such that Y is strictly less than X. Okay, that's the initial segment of that element. So this is telling you that if you have two well-ordered sets, alpha and beta, this is alpha and beta, either there exists a bijection between them, or alpha is somehow smaller. You can find X such that alpha is isomorphic to this one. Okay. Good. And proof proof is going to be let's try this thing. Let's give it exercise. And to do this thing, you need Zorn's lemma. Okay, and we'll prove Zorn's lemma in a bit, but use the idea. Use this idea. Use the idea. So you want to construct these isomorphisms, or like these bijections. You start with the initial ones. Okay, so you want a function, you construct partial functions. Okay, so you, for example, you start with this. So this is alpha and this is beta, and you have the minimum element of alpha and minimum element of beta, and then you construct a map that maps alpha to beta. It's not a full function, but it's a partial function. Okay, and then once you have this, you look at the next element, and then you map it to the next element. Okay, and then you keep going up and up and up. Okay, so you can do it because so you'll be constructing these good partial functions, and those partial functions form a partial order by itself. And then if you take a chain of those partial functions, and you can get to the maximum of that. The maximum of that would be stuck in would have the domain or the range to be equal to beta, alpha or beta, depending on which one is bigger. Okay? Good? Okay. So what's ended up happening, the kind of the well-loaded sets, you can like once you have this thing, you can define ordering between the well-loaded sets. But there is a little trouble, but it looks like you can define ordering between well-loaded sets because they're either equal. Then the isomorphic they're equal. Otherwise, one is less than the other one. Okay, but the problem is when you say that you can define ordering in the set of well-loaded sets. The trouble is the set of well-loaded sets, that thing is not a set. Okay, so we'll be like doing this whole thing and you'll avoid running into that. Okay, so like once you actually do that, I mean once you have this proposition, you're basically defining ordinals, a class that's like we have the like equivalent class of well-loaded sets that are isomorphic. That's an ordinal number. Okay, good. But let's go back. Let's get to the next topic, and now we are trying to get to the Zorn's lemma. And okay, uh,
You know, you know that always if I do pod, I don't even.
you're gonna get in big trouble. Okay. 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 Zorn's lemma. Now, so before getting into this, let me talk a little bit about axiom of choice. So you have the definition. This tells you have for any function from A to B and onto we have a function that's onto, then there exists a function g going from b to a, such that if you start with g and then you go back with f, then you get identity function in b. Okay, and picture. So this is your set b, and this is your set a. And this is your function. So like each element in here get mapped so the f maps some elements to this. Okay, and the axiom of choice is telling you that you can find a function g such that if you start here, you get back here, you can find, and then when you come back in f, you'll land back into the place you started. Okay, good. Now, and there is another one that you have seen. Let me call this thing formulation A. And you have seen the second one. Let A alpha in here be a collection of sets. Then there exists a function f going from the set lambda into the union, such that f of alpha belongs to A alpha for all alpha in here. Okay, so this is the one that you have, then that you're familiar with. You have a collection of sets, and you can pick one element from each set. Okay, and so exercise, prove that these two things are equal. Show that A if and only if B. This is actually easy to prove if you kind of look at this picture. Because in here, if you have a collection lambda like this, and then so this is going to look like lambda, and then these sets going to be like A alpha. This is your alpha. Okay, so you create a set A that looks like the union of A alpha, and then come back. Okay, and one direction is easy, the other direction you might need ordered pairs. I mean, you'll bump into a problem where this A alpha might not be pairwise disjoint. Okay, and then when you kind of put all the A alphas into the set A, you're going to lose them. Okay? Because then you create a set and take the union and you lose how to keep track of it. So you can use the ordered pairs to fix that issue. So that's our problem. Exercise 3, 4, 5. This is exercise 5. And this is exercise 6. And this is kind of the issue with the taste. Kind of by definition, the definition A is kind of prettier, like more beautiful than the definition B. Okay? And the reason being, the definition B refers to elements and the definition A doesn't. Okay? So if you know the notion of a category, like the first formulation, you can almost read it for groups. If you have two groups A and B, and then you have F to be a group homomorphism, which is onto, and there exists a group homomorphism from B to A, such that the composition is identity on B. Okay. It almost looks like you're not referring to elements. I mean, of course, we do it in here. It almost looks like this is like talking about the existence of some like right inverse of F. Right? If the F has right inverse and a left inverse, then it's we say A and B are isomorphic. But the axiom of choice is kind of telling that you have a right inverse. Okay. And it looks like you're not referring to any elements. Of course, the onto thing is referring to elements. So when I say that the definition A, I like it better, and here is the, look at this definition. Epimorphism. Epimorphism is F going from A to B is an epimorphism if for all G and H both are maps from B to C, if is an epimorphism if for all maps G and H such that this happens, and then G composed F equals H composed F implies G is equals to H. Okay, so this is giving a definition of a epimorphism. So, and this looks a little weird, but this is exercise 7. Show that epimorphisms are just onto functions. In the category of sets. Okay. So this kind of get rid of this issue with putting onto in here. Okay. So you can write the axiom of choice, get rid of this, and you write epimorphism. Then it's like fully clean and it looks like it works. You can like state the axiom of choice in the four groups easily. Okay? I don't know if it is true or false, but and it is by definition pretty if it is if you're not using elements. Okay? Good? So in other words, if it's onto, if you have an equation like this, you can cancel out from right. Okay. I mean, these are like trivial things when you do it in the sets. Okay. And then exercise 8, formulate and prove the version for one-to-one functions. Okay, and the formulation is one-to-one function is basically something you can cross off the other side. It's like f composed g equals f composed h, then g equals h. This is the one-to-one. Okay. Good. So this is the axiom of choice, and then yeah, and I gave a kind of a prettier definition. That's what happened in here. Okay. Now, let me state Zorn's lemma. Let be a partial ordered set called posets. Such that every chain is by definition totally ordered subset. This is the depth chain as an upper bound. Then, so if you have a partial ordered set that has this property, every chain is a totally ordered subset, has an upper bound. Okay, then the this L thing as a maximal. Okay. So remark chains can be empty. Okay. And exercise. Find which partial orders from our list satisfy satisfies the conditions. For Zorn's lemma. Okay. One of the things that's gonna satisfies one of the partial orders is the one that we have, like the linearly independent elements of a vector space V. Okay. That would immediately give you that any by applying Zorn's lemma, give you that any vector space has a basis. Okay. Good. Good. Now, so you have this definition. Oh, like notation. Notation is this. Initial segment. Initial segment of a chain C at X. So this is P X of the chain C is Y in the chain such that Y is less than X. So you have a chain, some partial loaded set. We pick a element in the chain and kind of the stuff that's strictly underneath it is called the initial segment. Okay? Now, proof. of Zorn's lemma. This is a useful proof, okay? And this is Nitika. Thank you for doing all this. I'll upload the video, okay? So you can watch it again, okay? We'll try to change the time, okay? Change the time. Thank you. I appreciate it. It's like if you used to going to sleep early and then staying up late is very difficult. Okay, now.
No, no, I'm not sleeping, so
Huh?
sorry. No, I'm not sleeping actually.
You're not sleepy?
No,
Really? Or you
Yeah.
bored? Then that's even worse.
no.
Okay. Okay, let's do the proof of this, okay? And you have to draw the pictures. So this is your partial order. It's like a giant thing. Okay. I draw it like this, and this means like this arrow means that this lines means the one element is bigger than the other. Okay, that's a partial order for me. Picture for it, and this taking if you take any chain like this. Okay, and any chain has a maximal element. That's what that's what's given for the in the Zorn's lemma. Okay. Good. And the conclusion, we want to show that there exists it's a maximal element for the whole partial order. And this is not guaranteeing that we have a unique one. I mean, there might be another one here, right? So the Zorn's lemma tells you that we satisfy if the partial order satisfy this property, if we take a chain and that chain has a maximal element, no, not a maximal element, not has upper bound. We take any chain and there is an element that's bigger than or equal to all the elements. If you have that, then the kind of, I mean, it's obvious in this regard. You take this and then you kind of, if this whatever this red point is not a maximal one for the whole partial order, that means there exists an element that's bigger than this, and you kind of go to that, and then you look for the next element, and so on. And if you keep going along that one path, you get to the place where you want to get to. Okay? So it's kind of, we have to kind of pick the next one and you pick the next one and so on and so on. Okay? Intuitively, that's it's not very difficult, right? But the picking the next one and picking the next one and not knowing how many times you have to pick, that's where the trouble is, and Zorn's lemma, the axiom of choice is going to help with that. Okay, so that's like the first the picture and the idea of the proof, like the intuitive idea. Okay, and now this is the second layer. This is again a wrong proof, but fixable. Okay, so proof. These are the best things. Okay, this is completely wrong, but has the correct steps, and it is fixable. Okay, these are the proofs we love. Okay, and by the way, this proof is I have the paper uploaded into the Piazza, and this is a very it's let me say the name of the person. This is a one-page proof by Jonathan Levin. And the key, I mean, you can tell like why this is a very beautiful proof, but I mean, it is avoiding some pitfalls or like some difficult techniques. The main thing that it avoids is transfinite induction. But yeah, we'll get to those things. Now, so proof by contradiction. We assume by contradiction. So you assume that this one does not have a maximum limit. Okay, assume that our partial order doesn't have a maximum. Okay, so if that is the case, we can carry out this construction. So let C be an element of this C. This is the set of chains. Okay, so let C be this thing, and C is element in here. So you pick a chain, and remember this chain can be empty. Okay. Now, so this is a chain, and so we get by the property, we get that C has a upper bound. Let A be an upper bound of C. Okay, and we note that this element A can be an element of C. The upper bound doesn't guarantee you that it has to be strictly upper bound. Okay. Now, but A is not a maximal element. Because the partial order L doesn't have any maximal elements. Okay. So that means there exists B in here such that B is strictly greater than A. Okay, have an element that's strictly bigger than this. So call this denote this element P by, let's call it f of C. Okay, so if you have a chain, sorry, it's a picture. So you have some chain here. That's your chain C. And then you have element A. The point is like we don't know if this element A is part of the chain C. Okay. But we can always find an element B that's strictly bigger. Okay. And the notation is a little confusing because the simple C stands for chain, but the A and B stands for elements of the lattice. Okay. So what we have done, so let's consider this map F delta is a map from C to C. F delta of a chain C, consider this one, chain C union B. It's F of C. So if you have one chain, now once you have this map, F delta, that allows you to create a bigger chain. Okay. Good. Zenith, question. So now, see now we're doing something that's similar to what we had in mind here. Okay. So if you have a chain, then if our partial order L doesn't have maximal element given chain, you can like create a bigger chain. Okay. This is pretty good. So now we consider this. We call it O. Just start with the empty set. So the empty set is a chain, and then you have this map F delta. Then you look at F delta of applied to the empty set, and this would give you a chain, right? And then you apply F delta again, that will give you even bigger chain. Okay, and then you go dot dot dot. So you keep doing this process, because you can now keep making the chain, start with the empty chain, and then you make it bigger and bigger and bigger. Okay. Now the good thing about this, all these chains are like now, they're like nested, one sits inside the other one. And they're all subsets of the L. Okay, and then these are all subsets, and then you can take the union of subsets. That's totally legit operation. Okay. Consider M is a union alpha in here of alpha. Okay. And you can claim, verify these two things. The first one, this M has to be a chain. Okay. This is easy to verify. So all you have to show that this thing is a total loaded subset. That means you pick two elements and you want to show that they're comparable. If you pick two elements, if you pick one element, that's going to belong to one of the chains, and then the other element is going to belong to another chain. But these chains are like nested, so that means both elements belongs to the bigger chain. That means they're comparable because the bigger chain is well loaded. The bigger chain is totally loaded. Okay. So this is a chain. But now, if this is a chain, this would give you, we can apply that F tilde operation to this. Okay. And you can create even bigger one. But this is, because if this is in M, then now we run into a contradiction. Because if this element in here, that means this guy is one of these alphas. Right? So that means this F tilde of M has to be a subset of M, because we're taking M is made by using the union of these guys. But this is a contradiction. We know that when you do F tilde, this operation, we are attaching an element that's not in the chain. Good. And that completes it. That's so you get the contradiction. So this means this shows that is a maximum. Okay. And there's a lot of things that went wrong in this proof, but all of those things are fixable. Okay. These are the best kind of proof that's out there. Okay. It gives you the intuition, gives you the big picture, and every step or like every other step is wrong, but it's fixable. Okay. And good. So what went wrong? So first of all, it looks like we never used axiom of choice. So the good. So the axiom of choice. So you're fixing few things. So fix. So the first one, using use of axiom of choice. So what we really have here, it is defining this function f. Okay, so this f is actually a function from this set C into L. Okay, good. And what's happening here? We are talking about how to define f of C for one element. So this is you're telling how to choose one element from a set, right? And you're jumping from that to this notation for a function, and this function, the domain of that function is not like finite set. It's this giant set, capital C. Okay, so that's where the axiom of choice get used. And if you want to go a tiny bit deeper, what's really happening? This argument is telling you you can define this set A of C, this set of elements B in L, such that for all x in C, B is strictly bigger than x. Okay, so this argument is telling you that set of elements B that are in our partial order that's strictly bigger than all the elements in your set in your chain C is non-empty. That's what this is saying. Okay, and so you have this collection of sets A of C, which are non-empty for each set C, and then this F we construct using axiom of choice. Okay, good. So this part is fixable, and then you can define these things. So, okay. Now, this is the really, really bad one. This dot, dot, dot. Okay. So, like we used dot, dot, dot. I know that you were like freaking out when I was doing it, but I think Senate was upset when I did it. So, yeah, these dot, dot, dots, we do it for like sequences, and you do it for sequences. If the defining rule is very clear, you do it like that. And somehow, like when you do it, it's because you can verify it using induction. Okay. And what we are actually using in this dot, dot, dot is transfinite induction. Okay. So what I kind of sold you is I mean, you can go through countable many steps, and then you can again create another bigger one. Okay, so you'll spend a lot of time creating this set. Okay, and this set has the property that you have a next element, next element, next chain, next chain, next chain. Okay, so this set O is going to be a well-loaded set. Because you know that we have the next element property in here, and let's give that as exercise 2. Why not? So this part is fine. Let's not go in there. I think like we have to reformulate what the having a next element means. And those are definitely equivalent to being well-loaded sets. So anyway, so like this set, this collection of chains, this one is a well-loaded set, and we have to construct this thing instead of doing this dot dot dot. Okay, and with the transfinite induction, what you're really doing, when you use transfinite induction, what you're really doing, you're like with induction versus transfinite induction. So the induction, you're creating a map f from n to some set A. Right, you have you use induction to do things like this, right? But if you're using transfinite induction, so in transfinite induction, you're not having the domain of your construction, your function to be not the integers but ordinals. The ordinals here. So this proof is this proof avoids use of ordinals. Okay, and that's a big deal, and that's why this proof is actually 19 recent proof. Okay, and notices of AMS notices, like one-page proof, and it's beautiful. And to understand the beauty, it's like you're learning some techniques and doing it, but to like really know why these techniques are beautiful is you're avoiding ordinals. Okay, good. It's like I'm teaching you to like how to fight a dragon, but you don't mention the dragon. So the dragon is the ordinals and transfinite induction. Okay, like one line answer is I mean all these things stay inside the set. So you can just use the unions to get it done. And actually, the proof that we're using here is very similar to the comparableness of ordinals proof. Okay, but that's happening inside the one set. Okay, now so the thing. So you construct of O. So I have written O here, but this is not ordinals, but this is like the set that kind of looks like ordinal. Okay. So, okay, let's go through the construction. The definition. For set subset of A of X is called conforming. If has these two properties, A is well loaded, in this proof I am using the less than or equal sign. Okay. I'm not done yet.
So when are you done?
It'll be 11:50. 11:52. He likes numbers. For all x in A, x equals f applied to Px. Okay, so this is the definition, but what's happening, he's trying to get at this confirming means he's trying to get at kind of initial segments of this set O. Okay, and so if it is the initial part of that, and remember, like all these things are elements of capital C, and so that's what he's trying to do. So he requires these things to be well loaded, not just total loaded, but well loaded. And also, if you take any element and then you look at this is the initial segment. And if you apply the function f, the next element thing for that initial segment, you land in x. Okay. So good. Now, okay. If A and B are two conforming sets, then A equals B, O one is an initial segment of the other one. Okay. See, this is like very, very similar to the comparability of the ordinals. Okay. Now, proof. I mean, you can assume that assume A minus B is non-empty. Because if A equals B, then we are done. And otherwise, if they're not equal and one of these things are, you have like a one that's bigger, one that's like we can assume this. And in this case, you want to show that the B is actually an initial segment of A. Okay. And in this case, you take X to be the minimum of A without B. Okay. Pictures. So the A, so let me draw it like this. This is my set A. And this is my set B. So an A and B are not equal. So we have, let's assume that it is like this. Okay. And the green here, and B goes off like this. Okay. So the X is the smallest element in A that's not in B. Something like this. They kind of branch off at this point. Okay. And for every element in A that's strictly smaller than X, that's a notation. Okay, that's like stuff that's in A that's strictly less than A, strictly less than S, X. And these things should be inside B. Okay. Because if you have an element that's not in B, that means we find the element that's strictly less than X that's in A without B. Okay. Now, what you want to show that claim, you need to show that. Show that is equal to B. Okay, so that means like this part doesn't exist actually, even though I draw it like this. Okay. So yeah, kind of running out of time, but let me do the fake proof. Okay. See, the idea is like these conforming sets, they're made up by using the function f. Okay. So you take element and then you apply f to it, and that's how you get the next element. So that means you cannot branch. So if you locate this element here, right? And by looking at the definition of A, because A is conforming, so let's find W. Let W be the be the maximum of let's say Y, such that Y is strictly less than X, Y in A, right? And you look at that element, so this is my W. And now if you look in here, take this guy to be Y, is the smallest element of P, and then the let me say let me do it. I mean, all this is wrong, but this will give you the idea. Okay, so let Y be the minimum element of B that's not in A. Okay, you go here, and then you look for the previous element. Let W to be, let me call it X minus 1, and that's also equal to Y minus 1. So you go to these things and you move one step below, and then you apply. So f of W is equal to X because A is confirming. Right, and also you will get f of W to be equal to Y because B is confirming. Because both these sets were constructed using F. So if you can go to the element below, if you can locate the element below, and then you can see that, oh, you cannot diverge, you cannot go in two paths because it's done using the same function F. Okay? And that would give you a contradiction. And of course the kind of the error in this argument is you cannot talk about Y minus 1. So if you're doing a Y minus 1, you're using a property. You look at all the elements that are strictly less than X, let's say, and then you look at the maximum. And the well-loaded sets doesn't have maximums. It's only minimum. It's like one-sided thing. Okay. So that's where this proof, like doing this thing, is wrong. But you can fix this thing too. Instead of going X minus 1 and Y minus 1, you can go back to the segment that's less than X, and also from the other side you can look at the set of elements that's strictly less than Y. Okay, so instead of like you don't have a W, but you work with the initial segments. Okay, and we'll go through the proof, and actually you can read the proof, it's readable. Okay, and that would prove the Zorn's lemma for you. And yeah, this is good. And I'll go through the proof again, okay? And yeah. Any questions? Any questions? Let me stop the recording.